In this third section of your notes over probability, we want to look at two last little ideas about probability. And the first of the two is going to be this idea of at least one of something. So at least one, if you're trying to interpret that, at least one means, you can say it a different way, one or more of something, okay? And if you're talking about like numbers, another way to talk about that is, you have one of something, or two of it, or three of it, or four of it, etc., etc., etc. Now, I want you to look at what I just wrote out. And basically, what's the only number that is not included in at least one? Okay, well, it is that you get none or zero, okay, of those items. And that is what we call the complement. It's basically like what's not included, what's the opposite, or what's missing to make out 100% of something. Well, that would be zero in this case right here. Okay, and we're actually, you may be wondering like, okay, where are we going with this? Why are we talking about the complement? There was a problem we did last week. Let me scroll back up to it real quick. We had a lady that had two flashlights, and it's this example right here. On the bottom of page, what page is this? It's in the middle of page 10. But it says right here in this example that you have a homeowner that has a 0.1 probability of flashlight doesn't work, so 10% that it does not work when she turns it on. And we said, okay, what's the probability that none of them work? And we found that the probability of none was 1% chance, okay? Well, then I asked you kind of a different question, and very similar question anyway, like what is the probability that at least one flashlight works, or what's the probability of her having light, her having a light that works? And we said it was 99%. Well, what are these two ideas connected to each other? At least one and none. What are those two ideas connected to each other? They are complements of each other. So we looked at that last week just a little bit, hinted at it, but this is actually what we're going to do is we're going to put it together and utilize it this week on this very last section of notes right here. Okay, so in the space below, we want to write the equivalent statement to the phrase all being defective, and then use that equivalent statement to write a statement that is the complement of all defective. So this is what we want to write for our equivalent statement. Well, of course, all defective this right here, if you wanted to write a phrase that's the same as that, okay, think about what all, we want to work in the words all or none, some of those types of terminology, at least one if we could. Well, all is the same as saying that none are good. If they're all defective, they all have a defect, that means that none of them are good, or you could say, none of them are free of defects. Okay, so none of them are good. Now, this is basically how you want to do the problems that are related to at least one and none. So if you want to get the opposite statement of none good, you're just going to take out the word none and replace it with the phrase at least one. So we take this word none, and to get the complement, we replace it with the phrase at least one. So we want to say the complement is at least one. And then you keep the same ending part, so at least one good. That is the opposite of none good, or you can think about it opposite. That's what I always think about, but a lot of people think of all and none as opposites right there. There is some logic. You can go through like the logic of is none and at least one total opposites of each other. It's kind of like that whole idea of like greater than. The opposite of greater than is less than, or a lot of people think that, but actually the opposite of greater than is less than or equal. So anyway, so it's that whole argument right there. You can think about it a different way. Logic equivalence. But anyway, we'll just call it complements for now. But all you have to do to get the complement of none is to put in the phrase at least one. So that's basically what we're going to be doing when we want to find these probabilities of at least one of something. And we're going to utilize those two ideas together. So we know that when you take the probability of something and its complement, you have to get 100%. Or if you're doing it as a decimal or fraction number, it needs to be 1. So we know that when we add the two ideas together, something and its complement, we have to get 100%. Well, if we want to find at least one of something, okay, the complement of that, of course, we know is none of that thing, okay? And we're going to take the none, we're going to find the probability of none first and subtract that from 100% or subtract it from 1. So to find the probability of at least one, we're first going to find the probability of none of that happening, okay? And the reason for that is, okay, there's a lot of ways that at least one can happen. One could happen if one thing, one of it happens, two of it happens, three of it, etc. Well, none only happens one way. There's only one way that none happens. Like everything fails or whatever. You have zero, one option, okay? We'll look at a problem below and talk about this in a little bit more detail, but, this is the easiest way to calculate the probabilities of none is to at least one is to take none, subtract it from 100%. So this problem down here says we have 3 births, so 3 children. We want at least one boy. So keep in mind that's what we're trying to find. Okay, I'm going to start this problem out. Probability at least one boy. Now, the way we want to do at least one, okay, let me talk about this real quick. Like at least one boy. There's a lot of ways that at least one boy can happen with 3 births. And these are just some examples over here. But you could have your first boy, your first child be a boy, your second child be a boy, your third child be a boy. And that's all the ways that one boy can happen. But at least one means one or more. Well, you could also have boys happen first, boys happen second, 2 boys. Or you could have boy, girl, boy. And you can list out all the different possibilities this way. Now, it won't be too bad for 3 children births because you only have 8 different possibilities total. Okay? But, if you had something like 4 births, 5 births, or, maybe you're flipping 5 coins, what's probability of at least one tails? These problems, you would not want to do it this way. So, let me show you what you're going to do. What I do is, I go ahead and say, okay, well, let's calculate probability of none boys. I'll put none, but it really none boys. No boys is what you want to say. Okay, and then I'm going to subtract that. Once I finally get whatever that is, I'm going to subtract that from 1. So it's kind of counterintuitive, but what does it mean for you to have no boys or none boys? That means you had 3 girls. You had a girl. They're all 3 girls, all girls. In your family of 3, all three children are girls. So if you're doing a multiplication rule, you have girl and girl and girl. And of course, the and means multiply because you're having 3 different trials. So you want to multiply. So we're going to have 3 little fractions that we'll be multiplying to get our final answer here for that part. And then we'll subtract that from 1. So we need 3 little fractions that we're going to multiply. And then, of course, you have 3 children. In the first childbirth, the first girl, you get a 1 out of 2 chance to have a girl. 1 of 2. And then the second girl, they're all independent of each other. So they're all independent trials. So you'll have the same probability of having a girl each time. You either have a girl or a boy. So it's a 1 out of 2 chance to have a girl. So first girl, second girl, third girl. Okay, that's no boys right there, which if you multiply those 3 together, you'll get 1 over 8. 1, subtract 1 over 8, well, 1 whole, take away 1/8 is 7/8. So that is your probability right there. I think that's 0.875, which is 87.5% chance of what happening. Okay. Well, go back. What we were trying to find in the very beginning, right there. We were trying to find at least one boy. So about 87.5% of the time, you're going to have one or more boys. So chance of at least one boy in a family of 3 children. Of 3. Okay. We'll go down and do another problem below. Okay, this problem right here says the FICO score is commonly used as a credit rating. There is a 1% delinquency rate among consumers who have a FICO score above 800. So the 800 really isn't that important. It's just telling you what people they're selecting. They're selecting people who have credit scores over 800. It says if 4 consumers, though that is important, though we are picking 4 people. If 4 consumers are selected with that credit score, find the probability that at least one of them is delinquent. Now, it does tell us in the problem that the probability of delinquent is 1%. It doesn't tell us what's the probability of not delinquent, so you have to use that information right there to get not delinquent, which we will eventually have this in the problem. Okay, that means there's going to be a 99% chance of not delinquency. Okay, and we'll get to where that's going to come in a second. Right here, I do have a little note to yourself just about regarding the multiplication rule when we get to picking the people. When calculating the probability here, it is assumed that 4 consumers is less than 5% of everybody that has a credit score over 800. Okay, basically what that means is I'm going to treat the events of choosing a non-delinquent as an independent event, which means like when you take one out, you replace it, okay, when we use the multiplication rule. So you won't have to worry about changing your fractions or changing your numbers that you multiply each step of the way. You're basically just going to assume it's independent events. So we want the probability of at least one of your 4, at least one delinquent. Okay, and this is the way you want to go about solving that. There's a lot of ways that one delinquent can happen in 4 people. It can be the first person you choose. It could be the second, third, fourth. You could have 2. You could have 2 of them be delinquent. And of course, that can happen in a lot of different places. So you don't want to worry about trying to think about all the different possibilities for one delinquent or at least one delinquent. What I would do is say, okay, let's go calculate the probability that none are delinquent. None of the 4 are delinquent. And then what I'm going to do with that probability is take it away from 1. Because those ideas, at least 1 and none, are complements of each other. If you add them together, they should add to 100%. So this is the easiest way to solve this kind of problem. Which, of course, if none of them are delinquent, okay, you have, not delinquent, not delinquent. You choose not delinquent 4 times. You're going to times that 99%. See where this came into play? You're going to take that 99% and multiply it by itself 4 times because you want 4 non-delinquents. You want not delinquent, none of them all being not delinquent. So all 4 are not delinquent. You can put this in your calculator a little bit different way just to save yourself some time. Since you're doing 99.99 times itself 4 times, you can just raise it to the 4th. The way that'll look on your calculator when you go to enter it is you'll take your calculator, do 1, subtract, and then do 0.99. You could do that in parentheses too if you wanted to, but you don't have to. And then raise it to the 4th like that. And when you hit enter, this is what we get right here, 0.0394. And that's basically saying 3.94% chance. And chance of what? What are we trying to find? 3.94% chance that there is what? At least one delinquent. Right there. Okay. We'll go down here and look at this one last example, and then we'll move on to our second little topic at the end of this section. Okay. This problem right here talks about the principle of redundancy used to improve system reliability. This problem says that there's a clock that has 86% chance of working on any given morning. We want to answer the questions below and then get to a conclusion. So the first question, number 1, says, what's the probability the alarm will not work? Well, if it's got an 86% probability of working, I think most everybody can figure this one out without even really me telling you. If it's got an 86% chance of working, well, what's the probability that the clock will not work? Oh, let me move my calculator here. Sorry. Sorry about that. So we have this problem right here just below. The principle of redundancy is used, and I got an 86% chance of the calculator working on any given morning. What's the probability of the clock not working? Okay. Actually, this might be a good exercise for you to do on your own. So you got probability of not working right there. Okay. That'll be something that you can do. And I'll post all the answers at the very end of the video. This might be a good one for you to do yourself. But let me walk you through these steps and what's going to be the setup here. Now, the second part right here says if you have 2 alarm clocks, what's the probability that they both, don't work? Okay? So you got probability that none work. That's your second part. And basically you're saying like none of your 2 work. None of 2 work. So you basically have not work and not work. Like that. So if you have 2 such alarm clocks, what's the probability that they both fail? Okay. So you'll have to take your 2 alarm clocks. They're identical. So you just take not work, and multiply them together, and you'll get that probability. Now, problem number 3 is a little interesting. But it says with 1 alarm clock, you have an 86% chance to wake up. What's the probability of being awakened if you have 2 alarm clocks? So the probability of waking up. Think about what happens that would cause you to wake up. Like what transpired in your bedroom? Well, either one or the other alarm clock went off, or they both went off. So basically that means at least 1 alarm clock at least 1 worked. And you can piece together now like how you'll use 2, your answer for number 2 of this to get the answer to number 3. Okay, and we'll give you a few seconds to work those out, and then you'll come back to the video and you'll see the answers. Okay, you can see that we have the problems worked out here. You have a 14% chance of the clock not working, and if you have none working, it's going to be a 1.96% chance roughly. And then what's the probability of waking up? Well, take your 1.96%, subtracting from 100%, and you'll end up getting 98.04% chance of waking up with 2 clocks. That's what the chance is of waking up with 2 clocks. Now, if you think about what's the chance of waking up with 1 clock, in the very beginning of the problem it says 86% chance with 1 clock. Does it increase your reliability of waking up when you have 2 clocks? Does it greatly do it? Is the results greatly improved? Yes, definitely greatly improved reliability. Okay, it's still it's not likely to not wake up, but there is a chance for it to happen. It's just way lower. It's like I said, now it's in the unlikely category. Whereas before, you had 14% chance. Now you have less than 2. You have 1.96%. So anyway, try those problems on your own, and then we'll look at the next little section of conditional probability in the next video.